Welcome, warm welcome. Thank you for being here. Get yourself prepared. Lock in for some calculus problem. Get a notebook. Grab yourself a pencil or pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you out of nowhere. Today we have a problem from the 2003 AP Calculus BC exam. And we're going to be using a chart here, as you can see. We're going to be asked some questions, including using Riemann approximation, a couple of other things. Okay, now let's get started, shall we? Give yourself like 12 to 15 minutes. You can go ahead and pause the video. Try to attempt this on your own first, and then when you're ready, come back and join us. We'll go through the rest of it. Fill in any gaps you missed. Maybe you have a better solution method than is going to be presented here. Maybe you can learn something from this solution method. Who knows? We are, after all, just in a void. All right, let's get started here. I see a chart, so I'm going to read this. This says diameter, okay? So it's the diameter or something. And this, the x values are distance. It's not time, Usually it's changing over time, but in this case we just have another distance as the x. So we're going to have to read the problem to see what's going on there. A blood vessel is 360 millimeters long, okay, with cross sections of varying diameter. Got it. So a blood vessel is not exactly just straight cylindrical. It kind of has like maybe some variation. You know what I mean? Has some variation to the diameter. It might be skinnier at the ends. In fact, it looks like it is a little bit skinnier. Oh, it has some fluctuation throughout, though. The table above gives the measurements of the diameter of the blood vessel at selected points along the length, which goes from 0 to 360, remember. And apparently the diameter represents a twice differentiable function at any given point along the blood vessel. So first, we're going to describe part A. Write an integral expression in terms of B that represents the average radius. Ooh, the average radius. The measurements are diameters, so we're going to have to take that into account. We want to represent the average radius. I don't know why I wasn't underlining any of this. In millimeters, between 0 and 360. So along the full length of the blood vessel, what is the approximate average, you can say, radius? So that's simply going to be the average value formula, which we would normally write like this. I guess in this case, it's going to be integral of capital B of x. Don't confuse those b's. Dx. And since we're going from 0 to 360, we're going to have 1 over 360. Right, but this gives us what? This gives us the average b of x, which means it gives us the average diameter. We don't want the average diameter. We want average radius. So we're going to have to get the radius from the diameter by dividing by 2. So we're going to multiply by an extra 1/2, and then we're going to integrate from 0 to 360 of b of x dx. Let's see, does it mention units? No, it doesn't have us discuss really anything about it. It also doesn't have us discuss this little trick that it's 1/2 of the average value, because the average value gives us the average diameter, not the average radius. So that's it for part A. It's a good integral for that. Part B, approximate the value. I had a feeling that was coming. Approximate the value of your answer in part A using the data in the table, and then using a midpoint Riemann sum with 3 subintervals. Okay, so we're going to go from 0 to 120, and then we're going to go from 120 to 240, and then we're going to go from 240 to 360, and those are going to be our rectangles, but the height of the rectangles comes from, ding, 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 the midpoint. So we're going to be using this as the height of those rectangles, this one as the height of that rectangle, and this one as the height of that rectangle. So we're going to say that the integral from 0 to 360 of bx, just the integral portion, that's the part that I'm approximating with rectangles, is nearly, let's see, these all have a width of 120, and then I can simply add the diameters. But again, we're looking for the average radius, so I'm going to have to take this integral and then plug it into that average value formula, and it's also multiplied by 1/2 because we want the average radius here. Okay, I'm stalling. So this is 84. Let's see what that's going to be. 10, 8, 0, 0? I believe that's what it's going to be. Let's see, we have 9600, and then we have 480. Ooh, so maybe not. We're going to have 10,080. It's a good thing I checked that. I wasn't fully confident about that. Yeah, right. Okay, because 960 plus 48 is 1,008. Got it. So this is the integral in terms of the diameter, but we need to plug that in here. So for part B, I'm going to say we need 1 over 720 times, what did we just get? 10,080. And I actually have a really good trick for this because we just came up with this calculation by multiplying 120. So why don't I just break it up again? This is really clever. Over 720. And this is just 1 over 6. So make your numbers smaller before you make them bigger. That's always the recommendation. Those are both divisible by 2. If you didn't realize they're both divisible by 6, I'm kind of walking you through that. And then these are both divisible by 3. So this is 14. Yeah, that's the average radius, and it's going to be in millimeters. And this makes sense because the diameters are all sitting around 28, 27, 29, 30, right? Half of that is 14, so seems reasonable. Perfectly reasonable. It does say show the computations. I'm surprised it doesn't say to use correct units on that one, but still you should use correct units on that one. Oh, interesting. Part C. Very interesting here. Okay, so it says using correct units. That's going to emphasize the units. Explain the meaning of this integral, which it says pi from 125 to 275 of b of x over 2 squared dx. Now, if we don't already see what the obvious truth is here, if you don't already see it, put this pi back in there. Why would a pi be in there, and why would a squared be in there? That's kind of like the circle area formula. Just not the integral, but the pi times something squared, right? And what do we have squared? We have b over x. So you have to remember, we just did 2 parts kind of discussing this and using this fact. This is the radius of the blood vessel. So if we're doing pi r squared now, we're talking pi r squared. We're talking about the game. We're talking about practice. Here is the radius that they're talking about. So what are we doing with an integral then? The integral adds up a bunch of these cross-sectional circles. So basically, again, if I have my diagram of my blood vessel, then from 125 to 275, each one of these is has some cross-sectional area. And so what we're basically doing is we're finding the volume of all of these by adding them all up together, right? There's a whole bunch of circles here. We're adding them all up together from this point down the vessel to this point down the vessel. And so we're finding the volume of this cylindrical, kind of cylindrical shape. It's not perfectly cylindrical. It's not uniform cylindrical because the radius varies. And that's exactly why we need to use an integral in order to calculate the volume. So we can calculate the volume within a certain portion of this blood vessel, which is kind of cool. So that means that this whole thing, our final answer is that this is the volume in the vessel from x equals 125 millimeters down the vessel to x equals 275 millimeters down the vessel. And maybe I should be specific because it did say to use correct units. So we're going to use correct units. Let's move this a little bit. Oops. Top of my 5. Let's see. It's going to be in... The radius is in... Let's see. Make sure everything's in millimeters. Yeah, diameter's in millimeters. So the radius is in millimeters. And the distance along the vessel is in millimeters. So we have millimeters squared times millimeters. Good. This is going to be in millimeters cubed. And they can use this kind of information for things like determining your... Or they can kind of estimate. I think they estimate your blood vessels actually from like pressure, from blood pressure models, I believe. I'm not really too sure. But yeah, they can determine like how much blood you can be pumping efficiently or not. If you have really, really, really small blood vessels, they're going to be like, yo, dude, you can't pump that much blood through your body. So yeah, just saying, that's a little digression. Part D says explain. These were explains. So the explanation for part C is like this whole thing. That's like y. It represents the volume, and it's in millimeters cubed. Yeah. Explain why there must be at least one value such that B double prime equals 0. Well, whenever we're guaranteed that something hits 0, that means that we're predicting it goes positive to negative, or negative to positive, right? So let's take a look at these values and explain what is exactly going on there. If you notice, in the first interval, the diameter is going up, then it's going down, then it's going up, then it's going down, and it seems to continue to go down a little bit, and then it goes up. Now, we don't know that it's going up the entire time during this interval, but we can track the behavior like that. And so we can kind of make a statement about the derivative and the concavity here. So let's take a look at the derivative, just the derivative of the diameter. So we say B prime, it's 6 over 60. So we'll say it's approximately 1 over 10. And then for this interval where it goes down, it's 2 over 60. So we'll say it's approximately negative 1 over 30. And then for this portion, it's positive 1 over 30. Now again, we're just talking about the derivative, not the second derivative yet, but we're going to use these values to make a statement about the second derivative. Then we have that it's going down by 4 over 60, which is negative 1 over 15. And then we have that it's going down a little more, actually. So, we could use this entire negative interval to say that it went down 6 over the course of 120 millimeters, and that would be negative 1 over 20. So we can do that to cover this entire decrease. And then at the end, it went up again, like 1 over 30, 1/30th. So these are the derivative values. If we keep track of the second derivative, then we can say that the second derivative must be negative at some point on this interval, because the derivative went from positive to negative. The only way for that to happen is if the derivative decreased. And if the derivative decreased, that means its derivative is negative. In other words, the second derivative. But on the other hand, we have that the second derivative, must have been positive at some point on this interval. I guess I'll put it in purple, because the first derivative increased. So we can use the differentiability, the fact that it's a twice differentiable function. That was a funny thing to see, but apparently it's important for the calculus here. we can make the statement that, in fact, I'll just type it. On the interval from 0 to 60, b prime is negative, but on the interval, I guess I should say somewhere on the interval, just to be very careful, but somewhere on the interval from 60 to 120, is that right? Am I talking out of my ass here? No, that's right. B prime is positive, therefore, somewhere on the interval from, and I'll put it in, proper notation, I guess, 0 to 120, B double prime must be positive. Similarly, B prime of x is positive somewhere on the interval 120 to 180. I believe that's where it was. Yeah. Therefore, B prime was increasing. Let's see if I can move this a little bit. I can't move it. Indicating that B double prime must be negative somewhere on 60 to 180. Therefore, since B is a twice differentiable function, B double prime must be continuous, so it must have crossed through 0 at some point on 0 to 180. Don't know exactly where it crossed it. I just know that it had to cross it somewhere. Let's see, I can make it more like that. All right, so kind of wordy explanation, but I just didn't want to just simply talk. I didn't have too much to draw. I had a lot more to say. So that will be our explanation for part D. Again, we know that the slope of B, we can even kind of sketch it, to be honest. We know that somewhere the slope of B is negative. Yeah, from 0 to 60. Sorry, from 0 to 120. Wait, do we? Right, yes, because it went up and then it went down. Went up and then it went down. That's the idea. Went up, then it went down. That doesn't prove that the concavity had to hit 0 at some point, but then it's going down, and then it's going to start going up. So there had to have been some point. Most likely it's on that interval from 6 to 120, it looks like. So I probably could have updated my answer to say somewhere between 6 and 120. 60 and 120, sorry. Yeah, I would say that somewhere in that interval, actually, is when B double prime had to have been 0. And that explains our reasoning. Yeah. I mean, there are other times where it fluctuates, so you could use all of these intervals pretty much because it seems to fluctuate. The derivative seems to fluctuate from positive to negative to positive to negative to positive. So just based on that, that means that the derivative itself is decreasing then increasing, and increasing then decreasing, which means the derivative itself has maxima and extrema, which means the second derivative has flat points or zeros. All right, I think that's enough blab out of me. This one was a little computation heavy, but there was also a very conceptual question in part C, where we had to identify sort of the area formula being used, and so that's sort of a volume integral. But didn't I just say enough blab out of me? All right, I'll see you guys next time in the Void.